So in AP Bio, in Unit 2, you probably have heard a lot about water potential. There's a high water potential, consequently, there's a low solute potential. And when there's a low water potential, consequently, there's a higher solute potential. So an easy way to think about it is that the more water potential, or the higher the water potential, the more water in a water to solute ratio. Now, to show this example, I here have 3 mason jars of water and 3 spinach leaves. One is going to be isotonic, one is going to be hypotonic, and one is going to be hypotonic. They have the same water potential. Here, in the hypertonic solution, the water has a low water potential. And here, in a hypotonic solution, the water has a high water potential. So because it's going to be a high water potential, we're not going to add any salt. For the isotonic solution, we're going to mimic the inside of the spinach. So we will be adding a half, oh wait, these all have 100 milliliters. So we're good all around, we're covering all ends. So this is a half teaspoon for every 100 milliliters of water. So we'll take that. Okay, one, try to rinse it out. Put it there. Then I'm going to take a teaspoon, or 2 teaspoons, or no, sorry, 2 tablespoons of water, and I'm going to put it here in our hypertonic solution. This is going to be our hypertonic. This is our hypertonic, and that is our isotonic. Now I'm going to mix these up, and I'm going to come back and show you what to do next. Okay, so what we're going to do here is we're going to measure weight gain or loss. If it gains weight, water went in. If it loses weight, water left. So surprisingly, these two actually both weigh 1.2 grams, and this one weighs 0.8 grams. So we're going to put each one, submerge it, or put it in the solution. We're going to shake it around to make sure, submerge. We're going to cover each one. And we're going to come back after 15 minutes and see what percentage of weight gain or loss each one had, if any. I'll be back. So it has been 15 minutes. The one that was in the isotonic. And look at that. Okay, I think I'm just going to do this. It is still 1.2. So for the isotonic solution, it's 1.2. And it stayed the same. Why? Because the water potential and solute potential, or solute concentration, both in the water and in the leaf, was roughly the same. Hypertonic solution, we're going to weigh it. Finally, we have our hypotonic solution, and it went from 1.2 to 1.4. From this data, one can conclude that when the water potential was higher, or there was more water in a water to solvent ratio, there was a net movement of water into the cell, which that would be a hypotonic. When there was more water on the outside than the inside, that would be a hypotonic, and the leaf gained weight. For the hypertonic, there was less water and also more solute, so the water left the cell because in the inside there was a higher water potential. I didn't get to weigh the hypertonic. I guess I lost that footage, but it did lose weight. It lost 0.5 grams. And then finally, our isotonic, because they both have the same solute potential and water potential, the movement of the cell, there was no net movement of water, neither out or into the cell. And there you have it, guys. That was a short experiment. This video is probably like 4 or 5 minutes long, so I appreciate you sticking around. And yeah, I hope this will help you understand water potential better.